At this point, we're going to now move into a bit of the mathematics. I'm going to show some of the high-level view of applied mathematics, mostly discovered by the brilliant mathematicians, French mathematicians in the 1700s, and I will also use a little bit of Riemann, basically the complex plane. If we have some region, let's say, and within this region we know everything that's going on within the region, which we'll denote by some scalar potential function psi. And psi is a function, let's say, of time x, y, z, which are the coordinates that describe or are measured within this system. And we also have a differential equation. And the differential equation describes the behavior of how psi changes within this region. And at the boundary, we have what we call boundary conditions. So if the statement is that if we know the differential equation, how things change within this region, and we know the boundary conditions, we can know everything that's going on within the region by solving psi. If, on the other hand, we happen to know everything that's happening within the region, and we know the differential equation, we can find the boundary conditions. Now let's say there is, let's say, a psi 1 differential equation 1 boundary conditions, and out here on this side we have a different psi 2, and we've got a set of differential equations 2 that describe outside this boundary. And in a way, what happens is that this psi 2 is equal, very similar to psi 1, it's actually the same thing, although a different set of differential equations on the outside than the inside, because the way that things happen and change are different outside the boundary than what they happen to be on the inside. This reminds us of a situation on the complex plane, where if we have the complex plane, we look at the transformation of z equals 1 over w. If we look at this particular transformation, we find that on the outside we have a situation or a region that would be, we'll call it valid, from the boundary condition to infinity, and on the interior we would have a situation where things would be valid from the boundary condition down to 0. So this is an infinite space here, semi-infinite space, but in reality if we use this particular transformation, we find that there is also a semi-infinite space in here. I'm just noting this particular transformation. We won't exactly be using it per se in what we're going to be doing, but the reason I'm bringing this up is because this then becomes the unit circle, and the unit circle in this transformation describes two semi-infinite regions. The psi's are very similar, if not the same, two different differential equations, and so the real thing is what we're looking for is the boundary conditions that divide the two regions, and it looks very much like the unit circle is going to be extremely, extremely important. So this is the attack, if you like, and how we're going to do it. We know psi, we know the differential equation, and we now need to find the boundary conditions that we're going to be looking for.